Ethers and epoxides. Introduction. Organic compounds having COC as the functional group are called ethers. Their general formula is ROR-, where R and R- may be same or different alkyl or aryl groups, or one of them may be an alkyl group and the other aryl group. The divalent oxygen is also called the ethereal oxygen. Ethers in which the groups R and R' are the same are called simple or symmetrical ethers, while those in which the groups R and R' are different are called mixed or unsymmetrical ethers. For example, diethyl ether, symmetrical; diphenyl ether, symmetrical; ethyl methyl ether, unsymmetrical; methyl phenyl ether, unsymmetrical. Ethers may be regarded as the functional groups isomers of alcohols. For example, both dimethyl ether and ethyl alcohol have the same molecular formula C2H6O but different functional groups. Classification. Ethers may be broadly classified into the following three groups. First, aliphatic ethers, in which R and R' may be saturated or unsaturated groups derived from aliphatic hydrocarbons. For example, ethyl methyl ether, saturated; methyl vinyl ether, unsaturated; divinyl ether, unsaturated. Second, aromatic ethers, in which either one or both R and R' are aryl groups. For example, methyl phenyl ether, ethyl phenyl ether, diphenyl ether. Aromatic ethers are further subdivided into phenolic ethers and diaryl ethers. Ethers in which one of the groups is aryl while the other is alkyl are called phenolic ethers or alkyl aryl ethers. On the other hand, ethers in which both the groups are aryl are called diaryl ethers. For example, methyl phenyl ether or phenolic ether, diphenyl ether, diaryl ether. Third, cyclic ethers, in which the oxygen is present in a ring, are called cyclic ethers. They are further classified as simple cyclic ethers or crown ethers. Simple cyclic ethers. Cyclic ethers containing 1, 2, or 3 oxygen atoms in the ring are called simple cyclic ethers. For example, oxirane or ethylene oxide, oxidane, tetrahydrofuran, tetrahydropyran, 1,4-dioxane, 1,3,5-trioxane. Crown ethers. Cyclic ethers containing at least 4 oxygen atoms are called crown ethers because their 3D shape resembles the shape of a crown. They are usually named as X crown Y, where X is the total number of atoms in the ring and Y is the number of oxygen atoms. For example, 12 crown 4, 15 crown 5, 18 crown 6. Nomenclature. First, open chain or acyclic ethers. Common names. The common names of ethers are derived by naming the two alkyl or aryl groups linked to the oxygen atom in alphabetical order and adding the word ether. In case of symmetrical ethers, the prefix di is used before the name of the alkyl or the aryl group. Some aromatic ethers, however, have their special names. For example, methyl phenyl ether is called anisole and ethyl phenyl ether is called phenetol. IUPAC names. In the IUPAC system, ethers are named as alkoxyalkanes. The ethereal oxygen is taken with the smaller alkyl group and forms a part of the alkoxy group, while the larger alkyl group is considered to be a part of the alkane. The common and IUPAC name of some ethers are structure of ether, common name, IUPAC name. CH3O CH3, dimethyl ether or methyl ether, methoxymethane. CH3O CH2 CH3, ethyl methyl ether, methoxyethane. CH3 CH2O CH2 CH3 diethyl ether or ethyl ether ethoxyethane. Third, common name isopropyl methyl ether. IUPAC name is 2-methoxypropane. Diisopropyl ethers. IUPAC name is 2-proproxy-2-propane. Methyl phenyl ether or anissoles. IUPAC name is methoxymethane. Ethyl phenyl ether or phenetols. IUPAC name is ethoxybenzene. Diphenyl ethers. IUPAC name is phenoxybenzene. For further illustration, the IUPAC names of some other acyclic ethers are given below. 2-methoxyethanol, 2-chloroethoxyethane, bromomethoxybenzene, 2-methoxy-2-methylpropane, 3-methyl-1-pyroxybenzene. Second, acyclic polyethers. Long-chain polyethers are named as oxa derivatives of the alkane, corresponding to the total number of carbon and oxygen atoms present in the chain. For example, 2,5-dioxahexane, 2,5,8-trioxanonane. Third, cyclic ethers. Common names. In the common system, the three-membered cyclic ethers are named as oxides of the alkylene from which they are derived. For example, ethylene oxide or epoxide, propylene oxide, isobutylene oxide. The names of some cyclic ethers are based upon the names of their fully hydrogenated products. For example, furan converted into tetrahydrofuran, 4-H-pyran or 2-H-pyran converted into tetrahydropyran. IUPAC names. The IUPAC names of cyclic ethers CH2O whole N, where N can be 1, 2, 3, 4, 5, and 6 are given below. N is equal to 2 oxirane, N is equal to 3 oxetane, N is equal to 4 oxolane, N is equal to 5 oxane, N is equal to 6 oxipane. The italicized portions of these names are the suffixes used to represent the size of saturated heterocyclic rings other than with nitrogen atoms. In case of substituted cyclic ethers, the substituents are indicated by numerical prefixes with the oxygen atom getting number 1. Trans 2,3-dimethyloxyrane or trans dimethyloxyrane. 3,3-dichloro-2-methyloxidine, cis 2-chloro-6-ethyl oxipane. Oxa names. Cyclic ethers are also named as oxa derivatives of their corresponding cycloalkanes. For example, oxacyclopropane, oxacyclobutane, oxacyclopentane, oxacyclohexane, 1,4-dioxacyclohexane. Methods of formation. Ethers can be prepared by the following general methods. First, from alkyl halides. Williamson synthesis. This is one of the best methods for the preparation of ethers. It involves the treatment of an alkyl halide with a suitable sodium alkoxide. The sodium alkoxide needed for the purpose is prepared by the action of sodium on a suitable alcohol. The reaction in fact involves the nucleophilic displacement of the halide ion from the alkyl halide by the alkoxide ion by SN2 mechanism. Thus, 2R-OH plus 2Na gives 2R-ONa plus hydrogen. Sodium alkoxide plus alkyl halide gives ether plus NaX. This method can be used for the preparation of both symmetrical and unsymmetrical ethers. For example, sodium ethoxide plus ethyl bromide at 330 Kelvin on substitution gives diethyl ether. Sodium tert-butoxide plus methyl bromide on heating gives tert-butyl methyl ether. Similarly, alkyl aryl ethers, phenolic ethers, can be easily prepared by treating sodium phenoxide with alkyl halides. For example, Sodium phenoxide plus methyl bromide on heating gives anisole. Like halide ions, sulfate ion is a good leaving group. Therefore, in Williamson synthesis, alkyl halides may be replaced by alkyl sulfates. For example, sodium ethoxide plus dimethyl sulfate gives ethyl methyl ether. Sodium phenoxide plus diethyl sulfate gives phenol. Limitations: a proper choice of alkyl halide and sodium alkoxide to be used in Williamson synthesis is necessary in view of the following considerations. First, since a halogen attached to a double bond or an aromatic ring cannot be readily displaced by a nucleophilic reagent, therefore aryl halides are not generally used in Williamson's synthesis. Therefore, for the synthesis of simple alkyl aryl ethers, the reaction is carried out between an alkyl halide and sodium phenoxide and not between aryl halide and sodium alkoxide. For example, sodium phenoxide plus ethyl iodide on heating gives phenol plus NaI, and bromobenzene plus sodium ethoxide on heating gives no reaction. However, if the halogen is activated by the presence of electron withdrawing group at ortho and para position with respect to the halogen atom, such activated aryl halide can be used in Williamson's synthesis. For example, para-nitrobromobenzene plus sodium methoxide on heating gives para-nitroanisole. Second, we have stated above that Williamson's synthesis involves nucleophilic attack of the alkoxide or phenoxide ion on an alkyl halide. Now, depending upon the structure, alkyl halide may undergo substitution or elimination reaction. Therefore, for the success of this reaction, it is necessary that the alkyl halide used must be such which predominantly undergoes nucleophilic substitution. Since primary alkyl halides are more susceptible to SN2 reaction, therefore best yields of unsymmetrical ethers are obtained when the alkyl halides are primary and alkoxides may be primary, secondary or tertiary. For example, third butyl ethyl ether is prepared by treating ethyl bromide with sodium third butoxide. Sodium third butoxide, that is tertiary alkoxide, plus ethyl bromide, that is primary alkyl halide, on heating gives substitution reaction and gives third butyl ethyl ether. The above ether cannot be prepared by treating sodium ethoxide with third butyl chloride or bromide, since under these conditions an alkane. Example, isobutylene is the main product. With secondary alkyl halides, both substitution and elimination occur together, giving a mixture of ethers and alkanes. But with tertiary alkyl halides, only elimination occurs, giving alkanes. Thus, when a mixture of third butyl bromide is treated with sodium ethoxide, third butyl ethyl ether is not formed, but instead 2-methylpropene is formed due to elimination reaction. Third butyl bromide plus Na positive O negative C2H5 on heating gives 2-methylpropene isobutylene plus ethanol plus NaCbr. Due to steric hindrance, secondary alkyl halides also prefer to undergo elimination rather than substitution. For example, 2-bromopropane plus CH3CH2O negative Na positive at 330 Kelvin gives propene 79% plus 2-ethoxypropane 21%. Second reaction. Reaction of alkyl halides with dry silver oxide. Ethers can also be prepared by heating an alkyl halide with dry silver oxide. For example, ethyl bromide plus Ag2O on heating gives diethyl ether plus 2 AgBr. Second is from alcohols. Ethers may be prepared from alcohols as follows. First, by dehydration of alcohols. Ethers may be prepared by dehydration of alcohols either in the presence of acids or heated alumina. A. Acid catalyzed dehydration. Symmetrical ethers can be prepared by dehydration of alcohols with concentrated H2SO4 at 413 Kelvin. Alcohol plus alcohol and addition of concentrated H2SO4 at 413 Kelvin temperature gives ether plus water. Example: ethanol on addition of concentrated H2SO4 at 413 Kelvin gives diethyl ether plus water. The yields of ethers, however, depends upon the nature of alcohol, whether primary, secondary, or tertiary. Since in this reaction, two molecules of an alcohol lost one molecule of water, therefore it is better called as intermolecular dehydration. Limitations: though this method is useful for the large-scale production of ethers, it has two major drawbacks. First, the preparation of ethers is always accompanied by the formation of alkenes due to intramolecular dehydration of alcohol. However, in case of primary alcohols, the alkenes are formed only to a small extent, which can be further suppressed by using a large excess of the alcohol. In case of secondary alcohols, alkenes are formed in much larger amounts than ethers, but in case of tertiary alcohols, exclusive formation of alkenes occur. Thus, the order of dehydration of alcohols leading to the formation of ethers follows the sequence primary, secondary, and then tertiary. Therefore, dehydration of alcohols is used only for preparation ethers from primary alcohols. Second, this method is not suitable for unsymmetrical ethers because a complex mixture of ethers is always obtained. For example, 3 moles of alcohol plus 3 moles of another alcohol on addition of concentrated H2SO4 gives ether plus ether plus ether plus 3 moles of water. Mechanism: this reaction is an example of a nucleophilic substitution reaction in which protonated alcohol molecule acts as the substrate, water as the leaving group, and another molecule of alcohol as the nucleophile. The reaction may follow either first order kinetics SN1 or second order kinetics SN2, depending upon the nature of the alcohol used. In general, primary alcohols follows SN2 mechanism, while secondary and tertiary alcohols followed SN1 mechanism. B. Catalytic dehydration. Dehydration of alcohols to ethers can also be achieved by passing the vapors of an alcohol over heated alumina at 523 Kelvin. For example, ethyl alcohol on addition of Al2O3 at 523 Kelvin temperature gives diethyl ether plus water. Second, by the action of diazomethane on alcohols or phenols. Methyl ethers can also be prepared in excellent yields by the action of diazomethane (CH2N2) on alcohols or phenols in presence of tetrafluoroboric acid (HPF4) as catalyst. For example, tetrafluoroboric acid plus diazomethane gives CH3N positive triple bond NBF4 negative, which on further addition of ethyl alcohols gives CH3CH2 O positive H and CH3, which on addition of BF4 negative gives Ethyl methyl ethers. Third, from alkanes. Ethers can be prepared from reactive alkanes by the following two methods. First, direct addition of alcohols in presence of acids as catalyst. For example, 2-methylpropane plus methanol on addition of H2SO4 follows Markovnikov's addition gives 2-methoxy 2-methylpropane or third butyl methyl ether. The main disadvantage of this method is that sometimes the initially formed carbocation rearranges to the more stable carbocation, which then reacts with alcohol to form rearranged ether. For example, 3,3-dimethyl 1-butane on addition of H2SO4 gives two products. First, 2-ethoxy-2,3-dimethylbutane, that is the rearranged product, and the second is 3-ethoxy-2,2-dimethylbutane, that is the normal product. Second, indirect addition of alcohols or alkoxymercuration reduction. Alkanes readily react with mercuric trifluoroacetate in the presence of an alcohol to give alkoxymercurial compounds, which upon reduction with NaBH4 in basic medium gives ethers in high yields. For example, propene plus ethyl alcohol plus mercuric trifluoroacetate on addition of NaBH4 gives 2-ethoxypropane. This two-step process is called alkoxymercuration reduction or alkoxymercuration demercuration and gives ethers in accordance with Markovnikov's addition of alcohols to alkanes. The main advantage of this method over Williamson's synthesis are: first, the reaction does not involve carbocation intermediates and hence there are no rearrangements in this reaction. 3,3-dimethyl 1-butane plus ethanol on addition of mercuric trifluoroacetate and second is NaBH4 or base gives 3-ethoxy-2,2-dimethylbutane. Second, absence of competing elimination reaction. Fourth, from Grignard reagents. Higher ethers can be prepared by treating alpha haloethers with suitable Grignard reagents. For example, methoxychloromethane plus CH3MgI in the presence of dry ether gives ethyl methyl ether plus chloromagnesium iodide. Physical properties. First, physical state, color, and odor. Dimethyl ether and ethyl methyl ethers are gases at ordinary temperature, while the other lower homologues of ethers are colorless liquids with characteristics ether smear. Second, dipolar nature. Because of the greater electronegativity of oxygen than carbon, the CO bonds are slightly polar and thus have a dipole moment. Since the two CO bonds in ethers are inclined to each other at an angle of 110 degrees, the two dipoles do not cancel each other. As a result, ethers have a dipole moment of 1.15 to 1.3 dB. For example, the dipole moment of dimethyl ether is 1.3 dB and that of diethyl ether is 1.18 dB. 3. Boiling points. Ethers are isomeric with monohydric alcohols, but their boiling points are much lower than the isomeric alcohols. This is due to the reason that unlike alcohols, ethers do not form hydrogen bonds. As a result, ethers do not show molecular association and hence have lower boiling points than the corresponding alcohols. Further, the weak polarity of the CO bonds does not appreciably affect the boiling points of ethers, which are about the same as those of alkanes with comparable molecular masses. Compound diethyl ether, molecular mass 74, boiling point 307.6. Compound N-butyl alcohols molecular mass is 74 and its boiling point is 390 Kelvin. Compound is N-pentane, its molecular mass is 72 and boiling point is 309.1 Kelvin. Fourth, solubility. Ethers containing up to 3 carbon atoms are soluble in water. The solubility of other lower ethers in water is comparable to those of corresponding alcohols. For example, like ethanol, dimethyl ether is completely miscible with water. Similarly, both diethyl ether and N-butyl alcohols are soluble in water to the same extent. Example 8 gram per 100 gram of water. The solubility of lower ethers in water is due to the formation of hydrogen bonds between water and the ether molecules as shown below. As the molecular mass increases, the solubility of ethers in water decreases due to a corresponding increase in the hydrocarbon portion of the molecule. Ethers are, however, fairly soluble in common organic solvents such as alcohol, benzene, chloroform, acetone, etc. Fifth, density. All ethers are lighter than water. Chemical properties. Ethers are relatively inert compounds, almost as inert as alkanes. Under ordinary conditions, they are stable to bases, dilute acids, catalytic hydrogenation, and to most other reducing agents. This is due to the reason that the functional group of ethers does not contain any active site in their molecules as compared to hydroxyl group of alcohols and phenols, even though the oxygen atom in both these functional groups contain two lone pair of electrons. However, under specific conditions, ethers undergo the following reaction. Reaction of ethereal oxygen. On account of the presence of two lone pairs of electrons on the oxygen atoms, ethers behave as Lewis bases and thus undergo reactions involving the formation of coordinate bonds as discussed below. First, action of concentrated acids. Formation of oxonium salts. The oxygen atom in ethers has two lone pairs of electrons. As a result, ethers behave as Lewis bases and thus dissolve in cold concentrated inorganic acids to form stable oxonium salt. For example, ether plus HCl gives dialkyl oxonium chloride. Example, dimethyl ether plus HCl gives dimethyl oxonium chloride. Or diethyl ether plus H2SO4 gives diethyl oxonium hydrogen sulfate. Second, formation of coordination complexes. Being Lewis bases, ethers form coordination complexes known as ethyrates with Lewis acids such as BF3, AlCl3, FeCl3, Grignard reagents, etc. Diethyl ether plus BF3 gives boron in fluoride ethyrate. Or diethyl ether plus Grignard reagent gives Grignard reagent ethyrate. Due to the formation of these complexes, Grignard reagents dissolve in ether. That is why Grignard reagents are usually prepared in ethers. They, however, cannot be prepared in benzene because benzene has no lone pairs of electrons and hence cannot form complexes with them. Second, reactions involving the cleavage of carbon-oxygen bond. First, with halogen acids. Ethers are readily cleaved by hydroiodic acid or hydrobromic acid at 373 Kelvin to form an alcohol and an alkyl halide. For example, ether plus HX at 373 Kelvin gives alcohol plus alkyl halide. Diethyl ether plus HI at 373 Kelvin gives ethyl iodide plus ethyl alcohol. However, if excess of acid is used, the alcohol first formed reacts further with the halogen acid to form the corresponding alkyl halide. Alcohol plus HX at 373 Kelvin gives alkyl halide plus water. The overall reaction may then be written as ether plus 2Hi 373 Kelvin gives 2Ri plus H2O. Diethyl ether plus 2Hi 373 Kelvin gives ethyl iodide plus water. Similarly, cyclic ethers are readily cleaved by HBr or Hi to yield dihaloalkanes. For example, tetrahydrofuran plus 2HBr at 373 Kelvin gives 1,4-dibromobutane. Reactivity of halogen acids. The order of reactivity of halogen acids follows the sequence Hi is more reactive than HBr than HCl. As discussed above, the cleavage of ethers by halogen acids in fact involves the nucleophilic attack of the halide ion on the protonated ether molecule. Obviously, greater the nucleophilicity of the halide ion, more reactive is the halogen acid. Since the nucleophilicity of the halide ions follows the sequence iodide is more reactive than bromide than chloride. Therefore, the reactivity of the halogen acids follows the same sequence Hi more reactive than HBr than HCl. Mechanism. The cleavage of ethers by halogen acids occur by the following mechanism. Step 1. Ethers being Lewis bases undergo protonation to form oxonium salts. Step 2. The protonated ether thus formed undergoes nucleophilic attack by the halide ion either by SN1 or by SN2 mechanism depending upon the nature of the groups R and R' and the reaction conditions to form a molecule of an alkyl halide with the displacement of the weakly basic alcohol molecule. If the groups R and R' are primary, the reaction occurs by SN2 mechanism, and if secondary or tertiary, the reaction occurs by SN1 mechanism. Site of cleavage. The site of cleavage of unsymmetrical ethers by halogen acids depend upon the nature of the groups R and R'. The following cases arise. First, if both the groups R and R' are primary, the alkyl halide is always obtained from the smaller alkyl group. For example, ethyl methyl ether plus Hi at 373 Kelvin gives 3 gives methyl iodide plus ethyl alcohol. Second, if one group is methyl and the other is a secondary or primary alkyl group, the reaction occurs by SN2 mechanism. Due to steric hindrance, the halide ion always attacks the smaller alkyl group, example CH3 group, to give methyl iodide, while the bulkier alkyl group gives the alcohol. For example, methyl isopropyl ether plus concentrated Hi at 373 Kelvin follows SN2 mechanism gives methyl iodide plus isopropyl alcohol. Third, if one group is methyl and the other is a tert alkyl group, the reaction occurs by SN1 mechanism, and the formation of products is controlled by the stability of the carbocation resulting from the cleavage of CO bond in protonated ether. Since tert alkyl carbocation is much more stable than methyl carbocation, therefore the alkyl halide is always derived from tert alkyl group and the alcohol from the smaller group. Example methyl group. For example, tert butyl methyl ether plus concentrated Hi at 373 Kelvin follows SN1 mechanism and gives tert butyl iodide plus methyl alcohol. It may be emphasized here that the high polarity of the solvent present in concentrated Hi 57% has favored SN1 mechanism. However, if the cleavage of tert butyl methyl ether is carried out with anhydrous Hi in ether, the low polarity of the solvent would favor SN2 mechanism, and hence iodide ion will attack the less hindered methyl group, giving methyl iodide and third butyl alcohol. Third butyl methyl ether in the presence of anhydrous Hi or ether follows SN2 mechanism and gives methyl iodide plus third butyl alcohol. Fourth, cleavage of alkyl aryl and diaryl ethers. In case of alkyl aryl ethers, the products are always phenol and an alkyl halide and never an aryl halide and an alcohol. For example, methyl alcohol plus iodobenzene is never prepared when anisole reacts with Hi at 373 Kelvin. But phenol plus methyl iodide is prepared when reacts with anisole at 373 Kelvin temperature. The carbon atoms of the phenyl group are sp2 hybridized, while that of the alkyl group are sp3 hybridized. A sp2 hybridized carbon being more electronegative repels the nucleophile, while a sp2 hybridized carbon being less electronegative attracts the nucleophile. In other words, nucleophilic attack by the halide ion occurs more easily on the alkyl group, leading to the formation of an alkyl halide and phenol. Secondly, a phenyl group is much bigger in size than an alkyl group. Therefore, because of the steric hindrance of the bigger phenyl group, the halide ion attacks the alkyl group, leading to the formation of an alkyl halide and phenol. It may, however, be noted that phenol is not converted to iodobenzene even with excess of Hi. Diaryl ethers are not cleaved by Hi because both the carbon atoms to which oxygen is attached are sp2 hybridized and hence repel the nucleophilic halide ions. Jessel method. Cleavage of alkyl aryl ethers by hydroiodic acid Hi forms the basis of Jessel method for the estimation of alkoxy groups such as methoxy and ethoxy groups. In such ethers, a known weight of the phenolic ether is treated with an excess of concentrated hydroiodic acid. The alkyl iodide produced as a result of cleavage of ethers by Hi is treated with an ethanolic solution of silver nitrate. The precipitate of silver iodide thus formed is filtered, washed, dried, and weighed. From the amount of AgI formed, the percentage of alkoxy groups can be estimated. Second, with sulfuric acid. On heating with dilute H2SO4 under pressure, ethers are hydrolyzed to alcohols. Ethers plus water at on reaction with dilute H2SO4 on heating under pressure gives alcohol. Diethyl ether plus water in the presence of dilute H2SO4 and heating under pressure gives ethyl alcohol. Second, when heated with concentrated H2SO4, ethers react in the same manner as with halogen acids to form an alcohol and an alkyl hydrogen sulfate. For example, diethyl ether plus concentrated H2SO4 gives ethyl alcohol plus ethyl hydrogen sulfate. Secondary and tertiary ethers, however, form alkenes. Third butyl methyl ether in the presence of concentrated H2SO4 and on heating gives isobutylene plus methanol. Third, reaction involving the alkyl group. First, reaction of air and light. Autooxidation. Formation of peroxide when exposed to air and light for a long time. Ethers are oxidized to form hydroperoxides or simply peroxides. Diethyl ether plus oxygen on the presence of light gives 1-ethoxyethyl hydroperoxide. It is a free radical reaction and oxidation occurs at the carbon atom next to the ethereal oxygen to form hydroperoxides. These peroxides are very dangerous compounds since they decompose violently at high temperatures. Therefore, serious explosions may occur during distillation of all samples of ethers if peroxides are not removed. Presence of peroxides in all samples of ethers may be detected by shaking them with a freshly prepared solution of FeSO4 followed by addition of KCNS. Appearance of a red color indicates the presence of peroxides. A simple method to remove peroxides is to shake an odd sample of ether with either an aqueous solution of Ki or a ferrous salt. When ether peroxides are reduced to ether and iodide ion is oxidized to iodine plus Fe2 positive salts are oxidized to Fe3 positive salts. Second, halogenation. Ethers react with chlorine or bromine to give substitution products. The extent of halogenation, however, depends upon the reaction conditions. For example, diethyl ether reacts with chlorine in dark to give alpha dichloro diethyl ether. Diethyl ether in the presence of chlorine dark gives alpha chlorodiethyl ether. In the presence of chlorine dark give alpha dichlorodiethyl ether. However, in the presence of light and excess of chlorine, all the hydrogen atoms are substituted to give perchlorodiethyl ether. Diethyl ether plus excess of chlorine in the presence of light gives perchlorodiethyl ether plus 10 moles of HCl. Epoxides. Three-membered cyclic ethers are called epoxides. In the common system, they are called alkyl oxides, but in the IUPAC system, they are called either alkene oxide, epoxy alkanes, or oxidants. For example, epoxy ethane or ethene oxide, ethylene oxide, cis 2,3-butane oxide, or Z2,3 epoxy butane, 1,2 epoxy cyclohexane or cyclohexene oxide, epoxy methylene cyclohexane or methylene cyclohexane oxide. Synthesis of epoxides. There are two main laboratory methods for the synthesis of epoxide. These are first epoxidation of alkanes. Alkanes on treatment with peroxy acids, also called peracids, such as perbenzoic acid, metachloropurbenzoic acid, peroxytrifluoroacetic acid, etc. in an inert solvent such as CH2Cl2, CHCl3 or CCl4 gives epoxides or oxidants. Due to the formation of epoxides, the oxidation of alcohols with peracids is commonly known as epoxidation. For example, alkene plus peroxy acid in the presence of CCl4 is epoxide plus acid. Example, ethylene plus peroxybenzoic acid in the presence of CCl4 gives ethylene epoxide plus benzoic acid. 2-methylbutane plus C6H5COOH in the presence of CCl4 gives 2,2,3-trimethyloxyrane plus benzoic acid. Cyclohexene plus metachloroperoxy benzoic acid in the presence of CH2Cl2 at 278 Kelvin gives 1,2 epoxy cyclohexane Mechanism. Peroxy acids act like electrophiles and the reaction is believed to proceed by the following mechanism. Ethylene plus peroxybenzoic acid in the presence of CCl4 gives ethylene epoxide plus benzoic acid. Second, from halohydrins. When halohydrins prepared by addition of hypohalous acids, that is HOX or X is equal to Cl or Br, two alkanes are treated with the base, HX is eliminated and an epoxide is formed. For example, ethylene in the presence of Cl2 or water gives ethylene chlorohydrin plus QH gives ethylene epoxide plus KCl plus water. Cyclohexane in the presence of Br2 or H2O gives trans addition of HOBr gives trans 2 bromo cyclohexanol. In the presence of dilute NaOH gives 1,2-epoxy cyclohexane plus NaBr plus water. Mechanism. It may be noted that synthesis of epoxides by base treatment of halohydrates is actually an intramolecular Williamson synthesis. Manufacture of ethylene oxides. It is manufactured by passing a mixture of ethylene and air under pressure over silver catalyst at 573 Kelvin. Ethylene plus oxygen. An addition of silver catalyst at 573 Kelvin gives ethylene oxide. Chemical reactions of epoxides. Acyclic ethers and cyclic ethers containing 5 and 6 membered rings such as tetrahydrofuran and 1,4-dioxane are quite inert and are often used as solvents. Three-membered cyclic ethers, example epoxides on the other hand, are highly reactive. This is due to the reason that three-membered rings are highly strained. Example, they have considerable angle strength because of their highly strained nature. Epoxide rings can be opened by a variety of nucleophilic reagents under much milder conditions. Consequently, most of the reactions of epoxides are the ring opening reactions. These can be catalyzed both by acids and bases. First, acid catalyzed ring cleavage of epoxides. Due to the large angle strain, epoxides are readily hydrolyzed by dilute mineral acids at room temperature to form corresponding 1,2-diols or glycols. For example, ethylene epoxides plus water, an addition of acid gives ethylene alcohol, glycol. Similarly, hydrogen acids and alcohols in presence of acids can bring about the cleavage of epoxides. Ethylene oxide plus HBr gives 2-bromoethanol or ethylene bromohydride. Oxygen plus C2H5OH gives 2-ethoxyethanol. Mechanism. In the acid catalyzed hydrolysis of epoxides, the oxygen atom of the epoxide ring first accepts a proton to form protonated epoxide. The protonated epoxide then undergoes nucleophilic attack SN2 by water to give a trans 1,2-diol. Base catalyzed ring cleavage of epoxide. Unlike ordinary ethers, epoxides can also be cleaved under basic conditions, like ethylene oxide plus water on addition of a base gives ethylene glycol. Similarly, sodium alkoxides, ammonia or amines can also bring about cleavage of the epoxide ring. Mechanism. Due to greater electronegativity of oxygen than carbon, The carbon atom of the epoxide ring carries a small positive charge and hence can be easily attacked by strong nucleophiles such as hydroxide, alkoxide, phenoxide, ammonia, amines, etc. Regioselectivity orientation of cleavage of epoxides. Unsymmetrical epoxides or oxidants can undergo ring opening in two different directions and hence can give different products under acidic and basic conditions. In acidic medium, the nucleophile generally attacks the more substituted carbon, while in basic medium, the nucleophile attacks the less substituted carbon. For example, 2,2-dimethyloxidase plus methanol on addition of acid gives 2-methoxy, 2-methyl, 1-propanol. 2,2-dimethyloxidase plus addition of alcohol gives 3-methoxy, 2-methyl, 2-propanol. Although both the reactions occur by the same SN2 mechanism, the difference lies in the stability of their transition states. In the acidic catalyzed cleavage of epoxide, due to protonation, each epoxide carbon atom carries a small positive charge, the magnitude of which depends upon the substitution. Since more highly substituted carbon can accommodate positive charge better, therefore more highly substituted carbon has a fair amount of carbocation character and hence get attacked by the nucleophile. Thus, in contrast, in base catalyzed reactions, there is no protonation, and hence none of the epoxide carbons has a fair amount of carbocation character. Therefore, like SN2 reactions, the attack of nucleophile is controlled by steric factors. Evidently, the nucleophilic attack will occur preferentially at the less hindered carbon atoms. Stereochemistry of ring cleavage of epoxides. Both acid and base catalyzed ring opening reactions of epoxides occur by SN2 mechanism. Therefore, attack of the nucleophile always occurs from the backside, leading to the formation of a trans 1,2-diol. See reactions with Grignard reagents and organolithium reagents. Epoxides also undergo ring opening reactions with Grignard reagents and organic no lithium compounds. The addition products initially formed upon hydrolysis gives primary alcohols containing two carbon atoms more than the Grignard or the organolithium compound. The epoxide generally used in these reactions is ethylene oxide. Vinyl magnesium bromide plus ethylene oxide in the presence of dry ether gives addition products which on further addition of acid in the presence of water gives 2-phenyl ethanol. N-butyl lithium plus ethylene oxide in the presence of trihexane gives addition products which on further addition of acid and in the presence of water gives 1-hexanol. That's it. Thank you.